Welcome back to our lesson on area trapped between a function and the x-axis. You've already watched the videos or you've been in class for this packet we've been working on. The packet, just to remind you, looks like this. We were estimating area between a linear function and the x-axis with 4 right-hand rectangles, 8 right-hand rectangles, 16 right-hand rectangles, and then ultimately we did use geometry to find the exact area of the trapezoid, which was 64 units squared. And then we filled in a few blanks before the video ended, where we kind of decided that the smaller we make the thickness of our rectangles, the smaller we make delta x, the more accurate our area became. And as we make delta x smaller, the number of rectangles approaches infinity. So what we need to do now is make this, we need to pull back, make it a little bit more generic so it will work no matter what function we're using, no matter what interval we're trying to find the area on. So I've drawn this picture. Feel free to put this into your notebooks. It's sort of an aside just to recap what we were working on and to help develop the formula. And once we do this, we'll go back to the packet. But here's the problem that we've been working on the last day or two. And I sort of just modeled this out. You see me on the x-axis from 2 to 10. Here's my linear function, x plus 2. So what I want to do now is generalize this problem. So we know that if we draw the first right-hand rectangle, we know we start at 2. But really, whatever this value is, I'm going to call that A. We know that 2 is our A and 10 is our B. So this is like the A and the B here. Okay. So the first right-hand rectangle is always going to start its left lower base, left lower corner at A, and it's going to look like this. It's going to have some thickness, some delta x. You're going to wind up right here, generically. You're going to pull up on the right side. You're going to touch the curve. You're going to come across horizontally and down. So let's see if we can make this sort of generic. So I'm going to say that the area, actually, let me bring this up here. The area of rectangle 1 is going to equal delta x, some change in x, times f of x. But which x? So I'm going to get a little bit more specific. Instead of calling this starting point A, I'm going to call it x sub 0. My pens are running out here. X sub 0, which means my initial x value. If I do this, then I'm going to call the next x value here x sub 1. That way, the true height here I can denote as function when x is equal to x sub 1. So the area of my first rectangle right here will simply be length times width, so f of x sub 1 times delta x. Okay, so then we make our next rectangle. So the next rectangle would have the same delta x because we keep that consistent, and a new height, try to make this a different orange, and a new height, a little taller. So we've got the same delta x because that remains consistent, but now if I call this next x value x sub 2, then this would be a height of f of x sub 2, and so my new area, the area of rectangle 2 would be f of x sub 2 times delta x. And this would just keep going and going and going until I get to the end of my interval. So I'm just going to kind of do like a dot, dot, dot here and say that the area of my final rectangle, I'm going to call that area of rectangle N. That would be over this way. It would kind of come through here. It would shoot up here, grab the height, come across and down. And if you think about it, I would end up here at x sub n, which would make the interval before it x sub n minus 1. So this area right here of the nth rectangle, or the final rectangle, would be delta x times the function evaluated at that last x value, x sub n. So area of rectangle n would be f of x sub n times delta x. Okay, with a lot of dot, dot, dot in between here. So, getting to my formula now, like a generic formula I could use to model the area trapped between, well, I just need to add all of these areas up. So the total estimated area would equal f of x sub 1 times delta x plus f of x sub 2 times delta x plus dot, 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 because we know there are going to be more of them, and finish up at f of x sub n times delta x. Okay, now think about our sigma rules from the other day. Isn't it true that when you have different terms being added together, you've created a series, and this can be modeled with the Greek letter S, sigma. So how about if I say that my total estimated area would equal the sum as I runs from 1 to n of f of x sub I times delta x. So you can see here, I've now left my I open to change. First it will be 1, then it will be 2, then it will be 3, up to and finishing at n. So this right here kind of shortens up the first line. And this is still estimated area. Now, if I want the exact area, then I only need to do one thing, and that is place the limit as n approaches infinity in the front of the summation. And what that's going to do, x sub I delta x, what that's going to do is it's going to take my number of rectangles. It's going to let my number of rectangles approach infinity, which in turn is going to make them skinnier and skinnier and skinnier, thus having less and less and less error or overhang. So by doing this limit, you're going to take that summation and you're going to find total area trapped in the curve. Now the man responsible for this formula, his last name was Riemann. George Bernard Riemann. You can research him on the internet. He's credited with this, and this formula then is noted as a Riemann sum. So this is your Riemann sum formula. It's an alternative to finding area geometrically. If you look back in the packet, we did find 64 units squared using area of a trapezoid, but now we know that calculus offers an alternative. And it was really genius. Imagine, he just took a shape that he knew, like a rectangle, a very simple picture. He shoved these rectangles underneath a function and simply added them all together, added all these simple areas together to create total area, and then shrunk his error right here with the limit as n approaches infinity of that summation. I mean, it's quite genius, really. And here's the best part of it. As we move forward in this lesson, true, you could use geometry for a linear function because, of course, this created that trapezoid, which we already have a formula for. But let's say the function's not linear. Let's say the function is quadratic. We don't have a geometric shape for this right here. So what Riemann allowed us to do through calculus is find the area of irregularly shaped figures that geometry didn't have an answer for. So it's really quite genius, and it makes this Riemann sum something that we're going to investigate further. So here's what we're going to do. I am going to have you go to the next video. What I need you to do is take this knowledge that hopefully you've written down somewhere, and we're going to apply it now to number 6 in our packet. And we're going to start the next video right here, where we're going to find exact area, and we're going to say that the exact area, and we're going to copy this formula down, is the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I delta x. We're going to use this formula on the specific example we've been dealing with. We're going to find the area trapped between f of x equals x plus 2 and the x-axis from x equals 2 to x equals 10. So I'm going to need you to tune in to the next video to get this problem accomplished.